We're now going to cover the dynamics of multi-degree freedom systems. This video will be relatively short because everything we learned about the dynamics of single-degree freedom systems is going to be applicable to multi-degree freedom systems. Furthermore, in the last video we looked at how we can use the finite element method to formulate the equations of motion. So let's look at the equation of motion in the time domain. It's given here, and what I've done, you might notice that I've added the damping, linear viscous damping, in this equation. But other than that, we saw this in the previous slides. U is the n/1 vector of nodal displacements, which is time dependent. P is the n/1 vector of nodal forces, also time dependent. Ms and Ks are the mass and stiffness matrices, which we looked at in the previous video. And as discussed, the damping matrix is difficult to define, and we're going to cover that in a little bit. Now, if we want to convert this to the frequency domain, we follow the same approach as we did for single degree freedom systems. We assume U, which is a vector, U of t, is equal to a time-independent vector U times e to the I omega t. And P of t we assume is periodic as well. And so when we substitute that into the equation of motion in the time domain, the e to the I omega t cancels, just like we did before for the single degree freedom systems. And we end up then with an algebraic equation. Now, you may notice what I've done here is I have used linear hysteretic damping instead of linear viscous damping for the same reasons. It's more convenient in the frequency domain, whereas linear viscous damping is more convenient in the time domain. I will point out here that omega q is the wave frequency, the excitation frequency for us. So now let's consider the solution in the time domain. As you'll recall, one of the first things we did for the single degree freedom systems is to find the natural frequency, the undamped natural frequency, which was just square root of k over m. That doesn't work here because Ks and Ms are matrices. So to find the natural frequencies requires solving an eigenvalue problem, which is represented here. This is the undamped eigenvalue problem because we're not including damping. So we're going to be calculating the undamped natural frequencies. Now psi j is an n/1 vector of nodal displacements, and omega j is the natural frequency. There are up to n eigenvalues omega j squared and n eigenvectors psi j, also referred to as normal modes. There may be fewer, but there are a maximum of n. By convention, the undamped frequencies are ordered from smallest to largest, so omega 1 is the smallest natural frequency, and omega n is the largest natural frequency. The same interpretation that we had for the undamped frequency for single-degree freedom systems applies to multi-degree freedom systems. Now the vibration shape's different. It's new, right? Because we're talking about a system with more than 1 degree of freedom. And so psi j is the vibration shape at frequency omega j. The orthogonality and orthonormality of the eigenvectors is very important, and we're going to be using them extensively, these properties extensively, and so let's talk about them for a minute. If we look back at the eigenvalue problem, the equation at the top there, we see that there are n unknown values in the eigenvector psi j, the n unknown displacements. There's also an unknown frequency, omega j. So there are n+1 unknown values, but we only have n equations, right? This represents a system of n equations, this matrix equation. So we have one more unknown than we have equations. So we have to do something. So what we do is we scale psi j, we put a constraint on psi j to eliminate 1 degree of freedom, and then we end up with n unknowns and n equations that we could solve. So let's look at that in more detail. If we look at the bottom equation there, psi j transpose ms psi q, when j is equal to q, we see that that's equal to 1. That's not accidental. That's the constraint we impose. That's called mass normalizing the eigenvectors. So when we do that, when we put that constraint on the mode shape, psi j, then we've reduced the number of unknowns by 1. So now we have n unknowns and n equations, and we can solve them. So the orthogonality property is when j is not equal to q. So when psi j transpose ms psi q, j not equal to q, we see that's equal to 0. And similarly for k sub s. So that reflects the fact that these eigenvectors are mass orthogonal and stiffness orthogonal. Finally, when in the psi j transpose ks psi q, when j is equal to q, we see that's equal to the natural frequency. Okay, so let's use that in determining the equations of motion and solving the equations of motion in the time domain. The n mode shapes form a basis for the same vector space as u of t. That means that we can define any arbitrary u of t as a summation of the mode shapes psi j times some unknown coefficients yj. So yj is referred to as the non-dimensional generalized coordinate. Using this equation and the orthogonality and orthonormality properties from above, we can substitute these into the equation of motion, pre-multiply by psi j transpose, and we end up then with a system of uncoupled equations of motion. And so these are just scalar equations of motion. We have n of them, or however many eigenvectors we're looking at. And we see that it's the same form, exactly the same form as the single degree of freedom equation that we dealt with previously. So we see that we do not need to explicitly form C sub s. I've just used the percent damping C sub Greek C sub j in the equation. Now Pj star, let's look at Pj star. Pj star is psi j transpose times P. Now this is a reflection of how much the structure responds to the spatial distribution of the loading P of t. So if a mode shape doesn't respond very much to a specific spatial distribution of the load, then Pj star is going to be small, and it could be even 0. And if Pj star excites a particular mode substantially, then Pj star will be larger. So let's look at the equations, modal equations of motion, just rewriting them here. And we see, that, as I mentioned before, it's identical to the equation of motion for a single degree of freedom system. And so therefore, the solution and the characteristics of this equation are identical. The disadvantage of forming these modal equations of motion is that we have to solve the eigenvalue problem. But there are a lot of advantages. First of all, the mode shapes help us understand how a structure behaves, and understanding the natural frequencies also helps us understand how a structure is going to respond to a certain dynamic loading. For slowly varying loads, for example, wave loading, would be relatively very slowly varying, the response is going to be dominated by lower modes and frequencies, and so we can get away with not looking at all of the eigenvalues and eigenvectors. We can look at a subset. In other words, we can choose 1 up to m mode shapes and frequencies to include in our analysis, where m is typically going to be much less than n. And therefore we gain a lot of advantages for this. Now, because it's very efficient. Now, it's not going to be efficient for systems with quickly varying loads. So for blast and collision and those sorts of problems, we're probably going to have to solve the multi-degree freedom problem directly. Now, when we follow this approach with m less than n, we say that we're working with a reduced basis. So psi j forms a reduced basis. Okay, let's look at the damping matrix, because we've kind of glossed over that. We have seen that if we follow this modal, what's called modal decomposition, to form the single degree of freedom modal equations, we don't need to form C sub s. However, we do need C sub s if we're going to follow a time domain formulation of the multi-degree of freedom problem without modal superposition. A popular approach is to use Rayleigh damping, so-called Rayleigh damping, which is shown here, where it says that C sub s is equal to some coefficient times the mass matrix plus another coefficient times the stiffness matrix. This maintains the orthogonality of the mode shapes, obviously, because it's equal to some proportion of m and some proportion of k. So if we carry out the product psi j transpose cs psi k, we know that's equal to 0, and psi j transpose cs psi j is going to be equal to a0, because we've mass normalized the mode shapes, plus a1 omega j squared. So what this means is that the damping in mode j is going to be equal to 2cj omega j. So the psi j transpose cs psi j is 2cj omega j, Greek c. So solving for c sub j, we see that it's dependent on the two coefficients, a0 and a1, as well as the natural frequency. The coefficients are chosen by specifying the damping ratio in two modes for two different frequencies. So the damping in those two frequencies is going to be as specified by the CJ, and the damping in the other modes is going to vary a little bit. All right, that's the end of this video. The next video in the series is going to be over the fluid model, and Professor Hayat Dawoodi will be providing that lecture. I will return in the lecture after that, where we talk about the equations of hydroelasticity.